Okay, woo! Lesson 3. This is it. 8.3 will be over. All right. So, I'm going to do one more story problem, then we're going to tie up some loose ends. I just want to make sure I touch on. So here's the situation. We go out to investigate how many hours students study at home at Craig High School. We find out from a random sample of 100. By the way, you might have to write in random. I don't know if your notes actually said random. It is kind of important, though. That the mean is 6 hours with a sample standard deviation 2. With a 95% confidence, state the interval at which we would assume the true population exists. All right, so here's what I'm going to do here. I am going to just type it all out how I would do it. All right, so we will perform a 95% T confidence interval. By the way, did you notice I said T? How do I know it's T right away? With a sample standard deviation. So I don't know the actual standard deviation, right? So I have, let's see, X bar is 6 hours. My sample standard deviation is 2. N is 100. Right? And for kicks and giggles, DF is 99, right? Okay. Let's keep at it. All right, we'll perform a 95% T confidence interval. Come on, click in there. To see what the true average of hours a Craig student studies. Is this every night? At home. It's not very clear whether it's every night. All right. All right, cool. That's my statement. All right, now my plan. My plan, Stan? All right. My plan will be, is it random? Yes. Stated random sample of 100 students. Period. Is it independent? Isn't this fun, guys? Is it independent? 100 students. You know what? I'm going to say start off with yes. Yes, 100 students is less than 10% of the population at Craig. Okay? Because we have 1,700 roughly. Is it normal? And I would say yes. Because our 100 samples passes the central limit theorem of having 30 or more samples to be normal. Cool. All right. Delete, delete, delete. Oh. All right, now my do. All right, here's the fun part. All right. Oh, sorry, every once in a while I gotta take some time and actually write it all out. Best guess is 6, right? Plus or minus. Alright, now remember, I do not know the actual standard deviation, so this is going to be a t critical value. Degrees of freedom of 99, so let's find that page. Degrees of freedom of 99 does not exist, so I'm going to have to select 80, and I want to be 95% accurate. So I'm going to put in 1.99. That's actually really close. 1.99. Oh, why do I keep doing that? 1.99. All right. 1.99. And if we knew the actual standard deviation, it would be 1.96. So we're just making it a little bit wider. Times my standard deviation, and since I don't actually know it, is 2 hours. However, I did sample 100 students. Okay. So, I'm going to just calculate that out, put it in my calculator, and I'll be right back. Hey! Alright, so after I put it in my calculator, I got roughly from 5.6 to about 6.4. Alright, so what does this actually mean in the context of my problem? Alright, so I'm going to start off by saying I am 95% confident I have captured the true proportion, or not proportion, the true mean time, a Craig student studies at home to be between 5.6 and 6.4 hours. Okay, so did I put it in context? Talking about Craig studying. Did I talk about how confident I am? I am 95% confidence between that interval. Okay, good. Check, check, check. I think that might suffice. All right. So let's wrap things up and then we'll be done. All right. So there's one last little hurrah. All right. So let me skip ahead. Here's all the homework practice. Blah, 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 blah. All right. Okay. So we're going to have to sit down and just get a little bit of heart-to-heart here. First of all, you'll hear this word, what is standard error? All right. I just want to touch base on what a standard error is. Standard error is when we don't actually know what the true standard deviation is. Standard error is going to be this guy right here divided by the square root of n. Okay? This is standard error. Okay? So it's our sample standard deviation divided by the square root of n. That is standard error. I know it's just kind of these weird things every once in a while they start talking about. Now remember, margin of error is everything that you add and subtract. So the margin of error is going to be your critical value times your, well, actually, do we really want to be specific about this? Technically, it's your critical value times your standard error, right? Right? I mean, if we really want to be picky about it. Now, you can find some of this stuff on your sheet, and hopefully you found it. I'm going to click around here. But if you go to your formula sheets that we should all have, trying to find where inference, right here. Notice on the inferential statistics page, it says here's your confidence interval. It says here's take your statistic. There's your critical value, standard deviation of statistics. So they say this just to be careful because sometimes we actually do know the standard deviation, sometimes we don't. this would be your standard deviation of statistics. This right here would be your standard error. Okay, and the only difference is that guy right there. Right? Here we use a t-score. Here we would use a z-score. Question, what do we use here? Oh yeah, we always use z-score for percentages. Okay? All right, so hopefully that's clear. Okay? Last thing, and I don't like to do this because I've hammered it so hard, but we do need to talk because our normal test is going to get a little bit more complicated. Come on, where are we at? Okay. Our normal test is going to get a little bit more complicated. So previously, this was our normal test, and I mean, we actually did it. It says for means, we have to have sufficiently large, and we said n has to be more than 30. For proportions, we have to have 10 successes, 10 failures. That's basically what that means. All right, so for proportions, cool, we're going to stay the same. But for means, we're going to add a few more caveats. Okay? All right, now, I hate doing this, but we kind of already know this. There is one thing that trumps everything. If we take a sample size of like 1, we can still do a z-score or t-score if it's stated normal, right? Stated normal. If it's stated it's normal, I don't have to have it pass the 30 or more. All right, and hopefully you know that that trumps it. If it says it's normal, you don't have to worry about anything anymore, right? Well, then we get a little bit more in depth. All right, if n is less than or less than or equal to 15, all right, and it looks somewhat normal. All right. We know it's normal. Okay? And usually that's when they say, you know, it's approximately normal. Okay? So that's pretty much, these two are almost the same rule. But here's the deal. We already know the n has to be greater than or equal to 30. That's the Clt rule, right? Central limit theorem. That means no matter what the shape looks like, it's going to be normal. But we have this little gap here. What if n is like between this, 15 and 30 mark? Right? What if it's between this 15 and 30 mark? Well, we can still prove it's normal if it is only slightly skewed. Oh my goodness. Slightly skewed. Woo. Alright. Try writing with the mouse. And no outliers. So it could be slightly skewed. Alright. And if we select 15 or more. Remember, I don't know if you remember when we talked all about this in Chapter 7, I kind of showed you guys, we had this thing that was all humpy. And even after we sampled like 4 things, it was already starting to look semi-normal, right? So even if you have a little slightly skewed thing, if you sample between 15 and 30, if it says slightly skewed, I could have a sample between 15 and 30 and still call it normal. All right. So only if it's like whacked out and I know nothing about the shape, I have to make sure the CLT more than 30. Okay, this is only for means. All right, hopefully that kind of wraps up our whole topic, and maybe we'll play a little game later on. Have a good one, guys. Bye.